Yes, good morning everyone. Today we are starting chapter 3, which is the method and philosophy of statistic process control. From the second chapter, we are talking about the inherent to process quality. So in these chapters, we are talking about the method and the philosophy of the statistic control. So from the process quality, we need to do control, right? So statistics is one of the most important. Okay, what is the most important? This is a statistic. We use statistics to check the process control. So the process control, we control all the process, all the methods. So normally in the factory, they have many processes. So from the point, we need to use the mathematical or we can use the data from the statistic to analyze how the process is going to be. So in these chapters, we're talking about the method and the philosophy of the statistical process control. So, firstly, you have to understand what is the statistic process control. It is a collect of the tool that when they use together can result the process stability and variabilities. So here, there's two: stability and variability. Normally, stability is very simple. It almost equivalent to mean. Variability is almost equivalent to variance or standard deviation as you mentioned. Okay, so stable the process mean, reuse the variability. Why we need to reuse the variability? Whenever your production or fluctuating, go back. I mean the process, it doesn't go smoothly. So when you have maintained all the streamline that the process mean, almost to the process mean. I mean the product coming, let's say you are using the machine to cut the part with the 3 meter lengths, and you can repeat 3 meter length, 3 meter plus minus 0.01, 3 meter length plus minus 0.05. So almost equivalent to process mean. So I mean if you can reuse the variability, let's say you make the product with 3 plus minus 0.5 or 0.7 or 1, this is not good. This means your product will be something like this. Yeah, something like this. This is not good from the mean. This is a flexibility. This is a flexibility. So what the stability mean? They want you to make it something like almost the same to the process mean. This is what they needed. So from this one, we use statistics to check quality. So we are talking about the method and philosophy. So I hope you understand about our lecture. Okay. So in this, we have to use the 7 major tools. One we call histogram, check sheet. Okay. Histogram, you understand. Check sheet, you understand. You have a Pareto chart. I think you have to understand. Fourth, we have cause effect diagram, or we call fishbone diagram. This thing you understand. Okay, fishbone diagram. Fourth, we call defect constructed diagram. I mean, you use like point to know the concentration. Defect constructed diagram. And 6, we use the cluster diagram. Oh, sorry, not cluster, cluster diagram. And 7, the last one, we use the control chart. Control charts. Yeah, this is last one is the most effective and going to start this one. Okay. The chart and assignable cost, quality variation. Chart means sample and a chart. The process I mean the chance of the cost of the variations. Chance cost of the variations. It is a process that is operating with only a chance cost of the variation present is said to be in statistic control. A process that operating in presence of the assignable cost is said to be out of control. The eventual goal of the SP, called statistical process control, is reductions or estimation of the variabilities in the process by the identifications assignable cost. So what is assignable cost mean? What is assignable cost? Okay, what is assignable cost? When we talking about the control limit, we're talking about it. Assignable cost is the cost of the chance of the material that is jumped out of the control limit. So let's say this is all assignable cost. This is assignable cost. This is assignable cost. This is assignable cost. There's a point that jump out of the control limit we call assignable cost. So remember this kind of image. If you're talking about the control limit, what is what? So if you're talking about the control limit, okay, so mean if you plot something point out the control limit, this is a confidence interval. This is control limit. So if a point is jump out here, if the point is jump out here, it means this is truly that identify that the process in the operating in the present of assignable cost is said to be of control. Then you cannot control because it is jump out from the control limit. Okay? Yes, we call assignable cost. So this is a chance assignable cost of quality product. So from upper and lower control limit, you have to find out from sigma 0 and T1, T2, T3, T4 and so on. Okay? Okay. So the next slide. From the control limit, you understand? Normally we have control limit, we have upper control limit, we have lower control limit. Okay? Okay. So upper, lower control limit. Okay. So from upper, lower control limit, we're not going to describe. The graph is like this. Look. Okay? This is control limit. This is upper, lower control limit, lower control limit. Okay. This is very simple. In the control statistic situation, all the sample may fall between the upper and lower control limit. The mean, yes, fall inside. The out control situation mean a point that plot outside of control limit. The mean here something like this. Okay, this is something like this. Okay, this is plot point out control limit. This is called uncontrolled, in control. Okay, next. So this is we are talking about the hypothesis and control chart. I think you're not going to forget about these formulas. That we are talking about in chapter 2. This formula is very important. Sigma x sigma over V. This is a point estimation. Point estimation. Or the variant point estimation. From this example, we have the process to be assumed the true process mean, which is 1.5. Okay, which is 1.5. The process that is standard deviation is 0.15. The sample size is 5 taken. So the sample variant is going to calculate from here. 0.15 over 5 square over square root. So The estimate of the process variance is 0.067 watts. Okay. Yeah, this is no problem. I think you can understand. So we are going to conduct a very common formula of control limit from the upper limit, lower control limit, upper control limit, and lower control limit. Okay. From this, yes, X 1.5 is mean. Sigma, this is, you have to understand, this is the confidence interval. Okay. So, from the formula, you're going to, from this, you're going to, in mu plus minus L, or we call length, 3 sigma, 1 sigma, right? Okay. So L, it must be 1, 2, 3, until 6, something like this. Let's say you have 3 sigma, yeah, plus minus 3 sigma. This is the formula of homograph from from this chart, from control chart. Okay, 3 sigma. So let's say you have 3 sigma, mu plus 3 sigma, 2 sigma, 2 sigma, 3 sigma, 3 sigma, 4 sigma, 6 sigma. Okay. Okay, this is no problem. This is just an example talking about the relationship between the hypothesis and control limit. Okay, let's say this is control limit and hypothesis test. We are going to explain about this one more. This is not different from talking earlier. This is the control limit. Okay, this is the control limit. So the point plot something like this. Okay. This is control limit. The point plot something like this. So this is a normal graph. This is a normal graph. It's a normal graph. From the normal graph, this is the same for the normal graph. If you are going to select it from the sample size. Let's say the n size n is for 5. Then x1, 2 until 5. Okay. This is upper lower control. This is a muy mean that mentioned earlier, 1.5. This is 1.5 minus 3 sigma, 1.5 plus 3 sigma. Okay, this is upper limit. Right? Okay. This is nothing different. You're just comparing the relationship between control limit and the hypothesis test. Okay. The importance of the control chart. One is the most process do not operate in the static state control. Second, subsequently the routine and the alternate use of the control chart will identify the assignable cost. I mean, they will identify the assignable. Let's say as any point gamma, this is assignable that they identify. And if the cost of B is eliminated from the process, the variability will be reduced. So whenever you are start to find and then omit from the data, so the variability will start to be low. The variability is the signals. The control chart only detects the assignable cost, manage the operation, and the engineer action is necessary to eliminate the assignable cost. So when you found control chart cannot do anything. So the one can do to before you eliminate, you have to use the engineer to identify where or from. So one you find the root cause, you omit and then calculate again. Our control action plan, we call OCAPS, are important aspect of the success control chart used to refer to the process improve cycle. Okay. So the control chart, we have two control charts. We have two control chart. One control chart one we call variable, one we call attribute. Because a variable data, because of attribute data. Normally, this is talking about distribution, continuous distribution, discrete distribution. Okay, so variable and the attribute is differentiated by this chart. First for variable, this chart is applied for data follow the continuous distribution. Okay, follow continuous distribution. This is follow discrete distribution. Okay. So normally it's a quality characteristic distribution for the tenor and then measurement. Or the data, let's take example from this one. Let's say speed, temperature, velocity, retest, acceleration, and other methods, length. This is the data must be from the discrete, meaning from components or non-component. We call MG in the factory. We call it the good not confirmed. It's something like content. Okay. The two types of variable. The first one we're talking about the variable control chart, variability. It is show up control chart. That this control chart will show up control chart. Okay, just show up control chart. It's the more effective when the in controls data is stationary or uncorrected. Okay, this is what this way. Okay. So the popularity of the control chart is I will read from this one. The control chart is program the technique for the improving the productivity. The control chart affects in the defeat preventions. The control chart prevent the unnecessary control adjustment. The control chart provide the diagnostic information. Control chart provide the information about process capability. Yes. So this is not much different because we are going. I'm already showing you the general formulas, the general formula of the control limit, upper control limit, and lower control limit. Written like mu plus minus L sigma. It's very simple. Yeah, it's very simple. So, approximate 97 confidence interval control limit. So that means, let's say 6. If we have L number 3, okay, 3 minus 3, then 2, then 1, 91.7%, 95%, 68%. This is something like this. From the control interval. Actually, this one we have written 73. This is the most accurate one. 9.73. This is approximate. But sometimes many people is very fast. Family from 99.7%. This is my convenient and 73. It is the 3 sigmas. Okay. Warning control limit on the control chart. Warning limit if used on a typical set of the 2 standard deviation from mean. If one or more points fall between the warned control limit and the control limit or close to the warned limit, the process may not operate properly. The good thing, the warned control limit offer the increase the sensitively of the control chart. The bad thing is one control limit results in an increased risk of failed alarm. This is good thing and bad thing of one control limit. The sample size and the sample frequency. I know, I think you understand that the sample that I mentioned earlier, the sample is going to be, this is a sample. Okay, this is a sample. We have x1, x2, and xn. This is n is size. N we call size. In this is sample size. Okay, n is sample size. Okay, yeah, we can continue. So from the n size, the average run length is one of the important. Average run length is 1 over p. So p, what is p? P you have studied in the chapter 2. P is the probability that any point exceeds the control limit. I forgot something I've written here. P is point exceed the control limit. So P something like this. So let's say, for example, if you are talking about three thickness, that the confidence limit is about approximately to 99.70%. That means you have to calculate in this example a average run length is 1 over p. P is much from here. P is 0.027. 0.1, another one. So 0.0027 is about 370. So that means what? In every from the three thickness confidence limit, in every 370 pieces is about one we are going to or tend to or would be fall out control limit. This is the message from the average run length. So from here we go into the more detail. The average run length is a very important way to determine the approximate size, the sample and frequency. So the considered problem, the control limit is set to 3 standard deviation from the mean. The probability of the point beyond the control limit, again 0.0027. So what is the average length tell us? The average run length give us the length of the time that we plot in the control before the point outside control limit. If for our problem, even the process remain in the control, an out of control sign will be generated every say 170 samples on average. Sometimes it is more appropriate to express the performance of the control chart in terms of average time to signal, ATS. They say the sample are taken at a fixed interval. H is our part. We call ATS. ATS. We call average run length hours. Okay, this is a subgroup. I think you are okay. This is a subgroup for this one. Run up, run down for the patterns, control pattern. Each node pattern indicate our control limit condition. Okay, so you are going to go through by yourself. Okay, this is node. This is a mining for the 7 magnetic segments. They control the most effective when they integrate into the comprehensive SPC program. SPC program, I mentioned earlier, SPC program is one of the programs you are going to use for the statistical control, statistical process control. The program, sometimes they use Excel is one of the most simple one. You can use this program. Okay? Excel. If not, we have another software. that very popular in the world, but with license. Arena also maybe we use another software. I forgot it. I forgot the software. But Excel could be one of the tools that you can use. We can use with Avalo Code. Yeah, Avalo Code software. Excel. Okay, this is a record again for the magnitude process fan. We have histogram, steam lab check, Pareto chart, cosmetic diagram, defect concentration diagram, cluster diagram, and control chart. Check sheet, I think you understand about this one. Pareto chart, okay, this is Pareto chart. It is okay, Pareto chart. This is a cause effect diagram. You have to construct a cause effect diagram. We have sub and stack. Okay. Seem like fishbone diagram you have ever. Cost and effects. Cost from machine, material, blah blah blah. The effect like low production. Okay, this is effects. Okay, this is the defect of the concentrate diagram. This step how to the step and the feature. Some information about the concentration diagram. You can go through this one. This is some example. Okay, cluster diagram. This is some cluster diagram. Let us finish. Okay, finish for the chapters. Thank you for today. So for next week we are going to use we are going to continue our next chapter, chapter 4 by next week. Okay, see you.